Hello everyone and welcome back to another video. So we finished off in our previous video looking at Dalton's law of partial pressure. We looked at Henry's law in terms of how soluble these gases are within a liquid and how these gases will sort of move down their partial pressure gradient. What we're going to be doing is sort of following on with that, but trying to now apply it to sort of our physiology and how this actually works in terms of transporting oxygen and carbon dioxide around the body. So the first thing to look at here is there are partial pressures for our individual gases. Now, at this stage, I will be referring only to oxygen and carbon dioxide, mainly because they're the two key players in terms of gases in the human body. So the first thing I want to discuss is the partial pressure gradient for oxygen when we are in the alveoli. Now, we obviously do have dead space in the alveoli. We also do have dead space in the conduction zone, so looking at sort of the trachea and the bronchi and stuff like that. I'm going to be mainly referring to the dead space in the alveoli itself. So this is why the partial pressure of oxygen dropped from about 160 millimeters of mercury to 104 millimeters of mercury. Because remember, it's mixing in with that sort of old air that's still in the alveoli. Now, if we compare this to the partial pressure of oxygen in the venous blood, it's around 40 millimeters of mercury. So there's a big jump. It's around nearly 2.5 times the difference in partial pressure of the alveoli compared to the venous blood when we are looking at oxygen. Now, if we were to then compare this to the partial pressure of carbon dioxide, I mean, yeah, there's still a partial pressure change, but it's far less steep. You know, we're comparing 104 millimeters of mercury going down to like 40. That's a big jump. Whereas when we are looking at carbon dioxide, it's going from 45 millimeters of mercury to like 40. Yet, even though the partial pressure gradient is nowhere near as steep, carbon dioxide moves faster than oxygen. So how on earth does that work? Simply put, because carbon dioxide is way more soluble in water than compared to oxygen. So it's able to move a lot easier and it doesn't need such a gigantic gradient. So if we have a look at this image here, and again, I don't expect you guys to sort of memorize these numbers, but I do expect you to have a general understanding as to how these values are changing depending on where it is that we're looking. So a perfect example is that we are looking at the alveoli in the lungs here, and we can see the partial pressure of oxygen is around 104, whereas with carbon dioxide, it's around 40. So then as the oxygen is moving away from the lungs, so as we've undergone that gas exchange in the alveoli, we can see that our blood now has around 100 millimeters of mercury of oxygen and around 40 of carbon dioxide. So what's going to happen is that freshly oxygenated blood is going to move through our pulmonary veins, is going to enter our systemic circuit here and make its way to the tissues. Because again, that's the aim of the game here. We are trying to deliver oxygen and remove carbon dioxide from our tissues. So what we see here is at the tissues, the partial pressure of oxygen is going to drop right down to 40 millimeters of mercury. And what we see with the partial pressure of carbon dioxide, that's going to jump up to 45 millimeters of mercury. So what we are seeing here is that internal respiration, that gas exchange occurring between the blood and the tissues. Then our blood is going to make its way back through the venous system and enter into the pulmonary circuit here to come back to our alveoli for the overall purpose here of undergoing that external gas exchange to remove that old carbon dioxide to get in some nice fresh oxygen and begin this cycle all over again. Now, for our body to be able to move around oxygen and carry around carbon dioxide, most importantly with oxygen, what we have run into here is a little bit of a problem. Now, as I've discussed in multiple videos previously, is oxygen is really not soluble in water. Now, diffusion is an excellent way for moving a substance around. It moves from high concentration to low concentration, but that's really not going to work for us because with diffusion, the greater the distance, the slower the speed is. And we as humans are just far too big. Now, this means that we need a very specialized system to be able to bind and transport oxygen around the body. in comes hemoglobin. So hemoglobin is a very specialized protein. It's a globular protein that's found in our red blood cells. And what it does is it's basically the Uber driver for oxygen. It will pick up oxygen from the alveoli and help to drop it off at our tissues. Now, this is where, again, we run into yet another problem. So, do we want hemoglobin to have a high binding affinity or a low binding affinity? Stay tuned in our next video where we're going to dig deeper into hemoglobin and looking at how we are able to overcome this problem of binding affinity. Look forward to seeing you then.